slides. So that was a bit of a history for you guys. So so this is kind of some of this we talked about, right? So with the advent of internet, the data, the new kinds of data exploded with the advent of internet. It exploded on corporate infrastructure, and there was no way that the current infrastructure we had prior could have handled that. So then basically what the whole idea is distributed computing. Divide and conquer. Divide a big job into smaller chunks and have each chunk do their own work, and so on and so forth. So this is how I try to explain it. Is the big data definition is it's a lot of data, and we have to process it in a reasonable amount of time. And so our ability to store, process, and analyze that data using the older systems just was not going to work because of these three V's. And I'm sure you have heard these, Shrikant, Nilima, you guys have heard the three V's many, many times over, right? That the data being generated today, the volume is just too huge, and the speed at which that data is being created is too fast, and the types of data being created, it's just not relational database, relational rows and columns anymore. They are structured, semi-structured, they're XML, they're JSON, they're web logs, they're all kinds of formats and stuff being created today. So so uh, so of course our architecture had to change. Where is it coming from? As we talked about, social media, sensors, web logs, medical devices, car, planes, oil wells. So so it had to be done in a different way. So let me skip back. So this is kind of the Shrikant, this is kind of the way I like to show it, that before Hadoop, the architecture, and I have gone through that myself at GlaxoSmithKline, I saw that how anytime our data volume increased, and I'm still talking about pre-internet, what we did is we bought a bigger and bigger machine. We bought bigger and bigger machine, more hard drive, more whatever, and that's called scaling up. You know, and the vendors, and we had Teradata, we also had Oracle, and they loved it, right? So bigger machines, bigger and bigger machines, bigger licenses, bigger cost, and that was the current model. That was the old model, and what we call that is scaling up. It's just getting bigger, bigger, and bigger as your data need increases. But the distributed computing, and I'm a chemical and petroleum engineer, so I always give that oil and gas example. But so this is like a big tank at a refinery, and if you need to store more, you build bigger tanks. But the distributed computing model is more like a tank farm. And if you have passed by, if you had opportunity to see a refinery, you will see these tank farms. They don't have one big huge thing. They have tank farms which look kind of like this. And you can extend the metaphor to see these are as these are unique servers, right? These are unique servers, and they make together, they make what is known as a cluster, right? So that's a very important term, and you'll hear again and again in distributed computing that it's a cluster. It's a cluster machine. They're probably identical machines, don't have to, but just assume they're identical machines doing a tenth of, if there are 100 machines, each machine is doing 1/100th of the task, right? So you have to see it like that. And so then this guy, this guy is Dave Cuddy. This is me. I met Dave a few months ago at a conference, and we had a great chat. Great guy. So this guy and his team created Hadoop, and Hadoop was, he was saying his son's pet elephant. So, and his son used to call that elephant Hadoop, so he called it Hadoop. The key idea is to break the work in chunks and bring code to data, and we'll explain what that is. So when you talk about Hadoop, always there are two parts to it, right? One is the HDFS, the storage, the Hadoop distributed uh, file system, and that you can see. This is you can see the server farm. this as HDF. You can say this is HDFS. So together they create the Hadoop distributed file system. A big file, say a 100 terabyte file, one file, when it comes through HDFS, HDFS will break that into 100 chunks. It will do replication, but we'll come to that a little later. And but for someone looking at a file from outside, it will look like one logical file, right? My file dot log, right? And it's 100 terabytes. But HDFS will break that into uh, however many servers you have cluster, how many servers you have in the cluster, and it will break that into the however many pieces. So there is one piece, very important piece, is just the storage piece. Like if you're processing that big a file, where would you even store that file? And if you are old like me and had experience in old data processing, that used to be a big thing. If you have processed something that a big file like say 100 terabyte, you got to first have it stored somewhere before you start processing it. And that was not a trivial thing. Where would you store it? So this Hadoop distributed file system uh, is solve that problem by saying if you have bigger files, well, you can always add more nodes to make your cluster bigger so that each chunk of that file could reasonably fit on one machine, right? And uh, and that way you can see it can a Hadoop distributed file system could scale, infinitely. You just keep adding more machines, and there's no limit. Maybe you'll run out of money, but if you have a huge file and your boss wants to see this 100 terabyte file, I want to know the web trends of people coming into some Netflix or some website. I want to know and make some decisions where to place my content next morning, and I want that data processed tonight, and I cannot wait for a month. I want that tonight. So Hadoop is good at that, those kind of batch processing. So HDFS is one part, and this is going to be a quiz question later on. And you may have seen these in these kind of videos in YouTube and so on and so forth. So once you have placed the data, suppose you had a big file, like I said, 100 terabyte, and you have chunked it up, randomly cut it in 100 pieces and put each piece on one machine. Now, if you have to write a program to kind of count the number of visitors, or any analytical work you want to do that data, you can you can see it's not that easy. Yes, you have the file all over, distributed over the cluster, but the program which will count or which will sum or aggregate, which will do whatever you want the program to do, it's not that easy that one single program can coordinate the files which are on 100 different machines and somehow collate the results as one single answer.
Mm.
So there has to be a programming paradigm which will take the code, whatever the code you have. Say you're summing up all the unique visitors. That's what you have in that file. It's a unique visitors to the Netflix site, and you want to see how many visitors are from which geography, which region, right? That's what the task your boss has asked you to do. Hey, take this file, analyze it, and give me back the results and how many unique visitors I had in last week from India, from China, from US, from this state, that state. And all the data isn't there, you got to give me the result back. So you know that the way you write the code, if you're a SQL developer, everything is on one database, right? Even if it's Exadata, Teradata, the when you write in queries, to you it appears a single table, a customer table or weblog table, and you can say select count star customer table, unique customer group by whatever, right? Behind the scene, the database will go find where the data is and give you the answer back. Meaning the programming paradigm in SQL, it hides all the complexity to get the information to you. Whatever it does behind the scene, you don't know. It's a very simple programming programming paradigm, the SQL paradigm. The SQL is not going to work with HDFS, right? There's no database. You just took say, a raw text file, huge text file, 100 terabyte. You cut it into 100 pieces and put each piece on one machine, each machine. SQL is not going to work, right? So there had to be a different programming model. And what Doug and team did is they called that model map reduce, right? and yeah, I'm 100% sure you have heard of MapReduce. And so, and the whole idea is, if you basically it's a divide and conquer. That what you're saying that, hey, if I have this task of counting unique visitors, I I can send that code, right? Whatever the code is, however you write that code, and you write that in Java and Pig and everything, and we'll tell you that. And things have changed along that too. But whatever the code you write, let's say Java code, instead of having all the data come through that application server piece of code and get processed, no. In MapReduce paradigm, I'll take that code and position and copy that code on each machine, each node. So that's called taking code to data, right? You're saying I'll take my application logic, which is counting unique visitors for 1 week of Netflix visits, Netflix website. I will take that code and put that on each machine. Why would I do that? So that each machine can independently give me the results. Whatever data is on this machine server number 87, whatever it is, doesn't matter. It can count number of unique visitors on that machine, right? And it doesn't care what else is happening on the machine. It's gonna be concerned about what the data is stored. That part of the data from the Hadoop chunk, it's on the machine. It will just process that data, right? After the data is computed on any particular machine, now you know, and that process is called mapping, right? So it's mapping your code to the data. And what happens after that, as an output of the mapping process, as you can imagine, you will get a key. What the result set is going to be a lot smaller, right? It's going to be a key value pair. Key value pair is going to look like, probably you can kind of imagine, it will say, as I said, the problem was tell me the count of unique visitors by region. So it will probably say on this machine, India 500, China 600, US 700, Canada this 100. So that's a key and value, right? India equals 500. India is the key. And it does that only for that machine. Now you come back to this, and you guys can see me moving my mouse, correct? Since I can't hear you, I'm assuming you could. And so on this, say, machine number 37, it's the same thing. Data is randomly stored there,
Hey
hundredth
Sudhanshu.
of that data.
Hey,
And
hi Sudhanshu. We can't.
when the code runs or the map process runs, it come up with a key value pair on this machine. India equals 100, Canada equals 500, US equals 5,000, right? So each machine have their own answer set, which is in the form of key value pair, right? And uh, now you can imagine uh, that answer that each room, each node came up with had to be tallied somewhere, right? It had to go to some central place where all those numbers are going to get tallied. And that's what brings me to the hold on, that that architecture that actually there is a nice little, I have to, right? So what this is, and if you're with me, that the Hadoop architecture is that there is a cluster of machine. Each machine is called a node, right? And those are basically these are the workers. But on top of that, there is a master node, as you can imagine, like a hall monitor, like a project manager, like a controller, right? And there's one machine which is the controller, and the controller machine knows. It's called a named node, and you may have heard of that named node concept. Uh, so that name node is kind of the yeah, like the hall monitor, right, in a classroom. It knows when a job starts, it comes to the name node first, and the name node will distribute that file, the big file I was telling you about, 100 terabyte file, into 100 chunks. The name node knows which machine has what data. So it's tracking that. It's got the list. It's got a pointer, right? Like row number 85 has got data rows from this to that, whatever. So it's tracking that, which machine has got what data. And as each machine is delivering its results, it also sends it back to the same uh, a set of machines called reducers. So, and every time it's doing a job, it's letting the main controller know that, hey, I'm done with the mapping task on server number 85. Give me something else to do. Or the controller will say, okay, you have done your job. You're fine. Now we're switching to a reducer step. So what is a reducer step? Once I said that each machine has done its mapping. If out of 100 cluster, if 80 machines are suppose your mappers, and it's doing the basic job of counting the regions, unique customers from each region, right? And it's doing that, and it's got the name value pair. Now the name value pair from each machine has got to go to a set of reducers, set of machines, which will take all those input, key value pair from each machine, and kind of tabulate it, copy it all together. It's almost like someone gives you 100 Excel spreadsheet, and each spreadsheet has got a set of numbers, key value pair, and your job is to put it all together into one answer set. That's what a reducer does. It's basically aggregates. And so mappers and reducers kind of work hand in hand. And once the reducer has tabulated all that key value pairs from each machine, it will go back and tell the name node, as I was telling you, the master controller, okay, I'm done. I got, 17,000 visitors from India and this much from this and that much from that, and that is your final result. Doing it that way, doing that in parallel the way Hadoop does, is way, way more efficient than you would if you had one big scale-up type model, because then everything has to be streamed through that one big machine. And as your data need grows, you will need a bigger and bigger machine, and it will get more and more expensive. As those machines get bigger, they get very expensive. With Hadoop, the whole idea is that you can use open source. So Hadoop is open source, and you can use cheap commodity machines, just nothing fancy about them, and just process them in parallel. So now with that, and since I can't hear you guys, I'll just I'll, some of the questions that has come up in prior sessions, I will kind of clarify those. So as you know, hard disks fail. I mean, that's a big when Doug and team they designed Hadoop, there was a common understanding that there's a 10% failure rates of hard disks. The hard disks fail. If you have a machine and you're doing say 1/100th of the computation in a Hadoop file system, in a MapReduce paradigm, and that machine fails, data is gone, right? And that was not acceptable because you cannot lose data. So what Hadoop does, that when you write, when you take the 100 terabyte file I've been talking about, and you split that into 100 pieces, and each machine gets 1 terabyte, it does something better. It will copy the same 1 terabyte data to 2 other machines, and that's called replication factor of 3. Why does it do that? Because there's an inherent understanding that if you use cheap hardware, it's understood those hardwares have a failure rate, right? 10%, whatever, over the year. And so if it's written just once, then you are jeopardizing the whole system. So what Hadoop did smartly, that it understood it would fail. So it said, I will write that data not just on one machine, but 2 other machines. Now the name node knows, the controller I've been telling you about, that which machine has, you can say primary, there's no such concept, but which one is kind of the primary and which 2 are the backups, it kind of knows that, right? It kind of tracks that, and it's as part of the task tracker. And so it knows that even though machine number 12 has the main data, right, 1 terabyte data, but machine number 17 and machine number 25 also has that data. So in the event machine number 12 fails, either of those 2 machines can raise their hand and say, hey, I have the data, I can do the same job, and don't worry about it. And the processing continues, it never stops. Machine number 12, machine number 15 now, as you can imagine, has got extra work, right? It's got its original 1 terabyte file it has been processing, and now it's got additional load of because of the failure of machine number 12, right? So now it's got a little extra work. Meanwhile, some other machines can come up in the cluster automatically or manually. If you're in Amazon Cloud, those things happen automatically. Uh, then the work will again get redistributed and rebalanced across the cluster, and everyone is, back to the same thing. So that replication factor of 3 is kind of important. And so right when I say that, one question comes up. So then that means you have basically made the data 3 times bigger. Like 100 terabyte file, when it goes to HDFS, it turns into 300 terabyte, and that is absolutely correct. It will replicate, but the whole idea is because these machines are cheap and hard disk is cheap these days, no one cares. It's not worth talking about that you've taken 3 times as much disk. The space you have, the disk you have on your phone, it used to be on a server 20 years ago. So no one talks about disk cost anymore. No one talks about RAM anymore, RAM cost anymore. So it was okay that if the data gets triplicated, as long as it brings the fault tolerance and redundancy to the system, so that just because one machine fails, the show never stops. Show continues on. That's a quick introduction.